So we're going to talk about the electric field today. And it was originally going to include conductors, but that's going to get its own video because it would make this one a little bit long. Well, what do you need to know about the electric field? Well, we should learn what it is, because if we're going to talk about it, that's probably a good idea. And then we're going to learn how to diagram it. The electric field started out with pictures, and that's how we're going to get there. Then we're going to quantify it. And it started with this fella right here named Michael Faraday. Michael Faraday pioneered the idea of the electric field. He was the son of blue-collar workers, didn't really have much formal education, but managed to be one of the most influential people in all of electricity and magnetism. He's even got a law named after him, which we're going to talk about a little later. So, regardless, this guy, good guy to know. So what we're going to talk about today is how he thought that if you had a charge, you could visualize this charge as being surrounded by this field. And that any other charge that you put somewhere, if I put some charge Q star here, it would react to the field created by Q1. It made it a graphical way. It was pretty neat to look at. So what is this electric field? The force between charges can be felt, even though the charges don't touch. So Faraday, as we just mentioned, modeled this. You have a particle, some charged particle, and it's in some sort of field. And this field is going to tell this particle which way it's going to go, which is a really handy way to model this. And the best part is you can do this visually. So what we're going to say we have some charge right here. And we don't know what it is. If we put a charge Q right here, and we assume that Q is positive, the direction of the electric field is the direction a positive charge would go. This is very important. Which way would a positive charge go here? All right, yeah, it would go away from it. How about if I placed a positive charge over here? It'd go that way. Over here? That way. And you kind of get the idea. Why don't you fill out the rest of the circle, then we'll see how we match up. The answer is, no matter where you place a positive charge, it's going to go away from this positive test charge right here. So what happens if we have more than one? Let's say that we have a minus charge here, and a minus charge over here. And I'm going to say that this is minus 2. All right, so which way? If you put a positive charge right here at the top, which way is it going to go? It'll probably go in here. How about over here? Same thing, it'll go towards the negative charge because positive charge goes towards negative. But this charge is really bigger, and we've been showing this with arrows, so how would you show that this charge is bigger? Well, easy way is, it's got more arrows. So what you can see is if it was over here, it'd start coming down, and then it could pull towards this one. It would pull towards here, pulling here, pulling here. Why is this balance point not in the center? Why is it closer to this negative charge? Think about that and answer it real quick. Okay, then the other question is, see how there's no field lines here? What does that mean? If you put a charge right here, it's not going to do anything. There is no electric field. Your electric field is equal to 0. And likewise, if we came around here, you'd see some 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this one has 10 lines around it, and it has twice as much charge, which means this one over here on the left gets 5, and it's already got 3, so 4, 5. Now the other important thing to note is that these field lines, notice one thing they don't do. They don't cross. So this leads us to our rules. First rule, field lines always go from positive to negative. Second rule, more lines, you have a bigger charge. And what I like to call the Ghostbuster rule, field lines never cross. You do not cross the streams. And now I'd like you to try on this one. So pause the video, give it a shot, and then see how well it compares. You have a prediction, right? And it's on paper, not just in your head. Okay, I'll trust you on this one. So if a charge is here, it's going to go towards the negative. Right here, towards the negative. Let's see, it'll loop from here. It'll start coming in here, like this. It'll come here. If it starts here, then it'll curve towards this middle one. And eventually they'll come away from the positive, always away from the positive. And then, let's see, 1, 2, 3, 6 around each charge is what I've decided. So we'll put 6 around each charge. And there we go, an electric field. There's another video with a couple more diagrams. I'd like you to take a look at that one as well. So quantifiably, what is this? Well, the electric field is the force per charge. So if I were to write this out, I would say that your electric field, it is a vector, equals the force per charge. All right? The force per charge you're going to place. In this case, if we're looking at the electric field from 2, it is the force per charge of Q1. So what we look at this, we would say that force, or E, equals force over Q1 equals, using Coulomb's law, negative Q1, Q2 over R squared Q1, because we're dividing by this Q1 over here. R hat, remember that's the unit vector. What cancels? Well, Q1 and Q1. And we get that your electric field magnitude is just minus K Q2 over R squared. And that should be squared. Sorry about that. And this is also a vector, R hat. So let's say that we're in the center of a dipole, and a dipole just has 2 equal charges separated by some distance. Now it is a vector. It also obeys superposition. So it obeys superposition, which means when you have more than one, you just add the effects. All right. So again, we have to use the distance here. So this distance, I'm going to call this C, which equals square root of a squared plus b squared from our good old buddy the Pythagorean theorem. This distance is also b, or C, sorry. And then if we look, well, let's draw the forces. So the force diagram from this is going to, well, goes towards a negative, our electric field. And then the electric field from the positive is going to go away from the positive. And if you break this into components, you can see that the vertical components cancel. This would be some angle theta. This is also some angle theta. Your vertical components are going to cancel, which brings us to something. If you see symmetry, use symmetry. It makes your work so much easier. And if we were to find the electric field. So now I know that all I care about is this component over here. I'm going to say that E at that point, P, E at P, equals 2. I only care about this little x component right here, and it's minus x component. So 2 minus k q over r squared, and in this case this r is a distance c. Now since you only care about the x component, what trig function do you use here? If this is your hypotenuse, you want this side, so what trig function do you use? Okay, cosine, because it is adjacent, cosine theta. And this would be in the x hat direction. So it's just like the force vector, except you're just adding the electric field vectors. Now, we've been working with forces since first semester, and sometimes electric field, since it's new, is a little harder to see. So what we could say, if we want to find the force based on the electric field, we know that E is force per charge. We can just rearrange this and get that the force is equal to Q times the electric field. And you can do this a couple of ways. There's another video, in fact the next video you should watch has samples of this, so please take a look at that. So in conclusion, your electric field is just the force per unit charge. What I want you to take a look at, one other question, some kind of wrap-up questions. If you have some charge, we're going to call this Q1. Is there an electric field at point P? Even if there is no charge? And the answer is yes. The electric field exists from this point. The electric field exists here, even if there's no charge there. It's the way a positive charge would feel a force. Okay. What happens if the charge, what happens if Q of P goes to 2 QP? Does that change the electric field at that location? Well, no, because you would have, if electric field equals F over Q, if you have twice as much charge, you have twice as much force. So it would be 2F over 2Q, which is just the same. So the charge at P doesn't matter. There doesn't need to be anything at P for there to be an electric field. So please go watch the next video, and we'll talk more about this. We'll do some more numerical examples, and then we will move on. Thanks.